This lesson deals with parallel resistors and the current divider rule. You can find these notes in the course ebook in Chapter 2 starting on page 22. Let me define what it means to be in parallel. Two or more circuit elements are said to be in parallel if the voltage across these elements is the same. This leads to a property called the parallel resistance property. Let me just state it. If K resistances are connected in parallel, the equivalent conductance is the sum of the K conductances. What that means is that if you have these resistors all sharing the same voltage, and say R1 through R sub K are in parallel, then this could be replaced by a single resistor whose value is the sum of the reciprocal values of the resistances, in other words, the sum of the conductances, and then reciprocal. Now, why would that be true? If we have these K resistances in parallel, and they're connected to the rest of a circuit, and suppose that the voltage between terminals A and B is V sub S, then current has to come out of the rest of the circuit because these elements can only absorb power, and that currents have to come back around and come back into the terminal B. Let's assign a current in each resistor, call it I1 for R1, I2 for R2, all the way through I sub K for R sub K. Then the current I sub S, which is entering a node, equals the current that leaves the node. So I1 plus I2 plus I3 all the way through I sub K. But what is the current I1? Well, it's the voltage across it divided by the resistance. Be V sub S over R1. Same is true for R2, so V sub S over R2. And again, all the way through V sub S over R sub K. So you could pull out the common V sub S. What we're left with is the summation of 1 over R1 plus 1 over R2 all the way through R sub K. Let's call that reciprocal summation an equivalent conductance, G sub EQ. Right now, if we take that same box and now hook up in parallel with it a single resistor whose value we'll call R equivalent, and is equal to 1 over G equivalent, which is equal to the summation of 1 over the individual resistances. Of course, you write it this way too. And this is going to be the sum of the conductances G1 through G sub K. Let's take a look at some special cases like we did for series elements. Suppose you had only two resistances in parallel. We'll write that as R1 and then two straight lines in R2, where the two straight lines is from geometry indicating parallel. Using our previous property, we could then find R equivalent as 1 over G1 plus G2, and write that, of course, as 1 over R1 plus 1 over R2. Let's multiply numerator and denominator by the same two symbols, and that would just be multiplying by 1. And if I pick that to be R1, R2, then the numerator is R1, R2, and the denominator is R1, R2 divided by R1, which is R2, and then R1, R2 divided by R2, which is equal to R1. So having two resistors in parallel is the product over their sum. This only works for two resistors. You can extend it to three resistors by combining two resistors in parallel and then putting that in parallel with the other resistor, which is again is two resistors in parallel. Very common in electronics to see two parallel resistances or three. We're going to use this trick to get our results. It's a little bit easier to work with resistances than conductances because they're much larger numbers. Now, I can look at a special case of this previous one where the two resistors are equal to each other. So our R1, R2 becomes R1, R1 over R1 plus R1, which is R1 squared over 2R1. One of the R1s canceled with the denominator, and we're left with half the value of the resistance. We may find this useful is suppose that you want to have a 1 watt resistor of 1K. Now you could do this by taking two 2K resistors, which are each a half a watt apiece, and put them in parallel. 2K in parallel with 2K would be 1K, and now each resistor has the capability of a half a watt and then totally 1 watt. Take this idea a little farther to K equal resistances, and then our denominator, just using our property, would be G1 plus G1 all the way through G1K times. So we'd have K over R1, and that would just be R1 over K. K resistances in parallel is just 1 over K times the value of the resistance. Let's do an example. Suppose I have these three resistors in parallel, 18 ohms, 9 ohms, and 4 ohms, and I want to find the equivalent resistance looking into the terminals where these three are in parallel. Now, just taking our property, we would take the reciprocal of the sum of the conductances. So 1 over 18 plus 1 over 9 plus 1 over 4. Reciprocal will be R equivalent. Let's find a common denominator. Try 36. 1 over 18 is 2 over 36. 1/9 is 4 over 36. And 1/4 is 9 over 36. If we add up 2 plus 4 plus 9, you get 15. And then bring the 36 in the numerator, and that's the value of R equivalent. I'm going to reduce all of our answers to just decimal form, and that would be 2.4 ohms. Now, you could do the same problem on your calculator if you have a reciprocal key. division has a precedence over addition. So we're able to take 1 over 18 plus 1 over 9 plus 1 over 4, and then when you hit equals and then reciprocal again, you then get the 1 over summation terms. This is a very fast way of getting the equivalent resistance, just using your calculator. Now let's try the same example using the shortcut of 2 at a time. I'll take the first two resistors and take their product over the sum. So 18 times 9 is 162 over 18 plus 9, which is 27. And that turns out to be 6. And then we'll take the product over sum of 6 and 4, which is 24 over 10, and again get 2.4. And so this is another technique for getting an answer, just taking them 2 at a time. Our next property is called the current divider rule, and let me read it to you. If k resistances are in parallel, then the current through the jth element is equal to the jth conductance over the sum of the total conductances times the current that's coming out of this box and eventually leaving back again. And we notice in this theorem it's very much like the voltage divider rule, but the word parallel is replacing series and the word current is replacing voltage. As I mentioned in an earlier video, this is called duality in circuits. And the reason is that you can write Ohm's law as V equals IR, or you can write I is equal to G times V. These inner word properties have some real interesting things in circuit theory, and this is in a later course if you're interested. Now, why would this current divider rule be true? So again, hook this up to a box. There's a voltage here due to the circuit, and current has to come out of that box and go back into it because these can only absorb power. So it's generating power. All right, the current in the jth element is going to be the voltage across it divided by the resistance. Of course, that's just equal to V sub S because to be in parallel means you share the same voltage. You could write this as G sub J times V of S. Assign a current to resistor R1 as I1, resistor 2 as I2, and all the way through resistor R of K as I of K. The current I sub S enters the node, and I1, I2, through I sub K leave the node. We've got that summation of currents equal to I sub S. What's I1? Well, it's the voltage across it divided by the resistance, and that's V sub S over R1. But likewise for I2, it's V sub S divided by R2. And all the way through R sub K is V sub S divided by R of K. So you can pull out the V sub S, and you have the sum of the reciprocal of the resistances, which is the conductance. So just taking this equation and solving for V sub S, it's equal to I sub S divided by the sum of the conductances. Now substitute that V sub S into this equation, and we have that the current in the jth element is G sub J times I sub S over G1 through G sub K. And now just interchange G sub J with I of S and you have the property. Just like the voltage divider rule, there are special cases for the current divider rule. Let's take a look at a couple of these. Suppose I have two resistances in parallel, R1 and R2, and in parallel with that a current source I of S. Let's find the current in R1 and R2. Just using our property in the previous page, I1 is equal to I sub S times G1, the conductance of the current that we're interested in, over the sum of the two. The same is true for I2. It's going to be I sub S times G2 over G1 plus G2. So like the voltage divider rule, except now we're replacing current for voltage and conductance for resistance. But let's convert this into a resistive formula. G1 is 1 over R1, and G2 is 1 over R2. That would be our equivalent expression. Now let's multiply numerator and denominator by R1, R2. I just get R2 over R2 plus R1. For the second equation, R1 times R2 would just give me an R1. And then multiplying R1, R2 by this term, I get R2. And this term, I just get R1. I'm going to call this equation the resistive current divider rule, and this the conductive current divider rule. And the way to remember it is that if you want the current in resistor R1, you take the other resistor over the sum of the two. Now this only works for two resistances in parallel. And again, you can take multiple resistors in parallel and reduce them to a single pair of resistors in parallel. Suppose you had two equal resistors. You'd have R2 over R2 plus R2, which would be half the value. So what's interesting here, independent of the value of the resistor, we would have half the current in each. Take this idea through k elements in parallel. Again, just using the straight definition here, we would have, for the first case, G1 over G1 k times, and the second one, G2 over G2 k times, and the G2s would cancel, and you just get 1 over k. In a lot of electronics, we do use equal value resistors, and so this is a very quick way to do calculations too. Do another example. Let's find the current in this 20 ohm resistor. And what I've got is 20 in parallel with 20 in parallel with 10 if I put these two in series. The conductance of this element would be 1 over 20 divided by 1 over 20 plus 1 over 20 plus 1 over 10. And all that will be multiplied by 5 amps. Multiply numerator and denominator by 20 and you get 1 and 1 plus 1 and then plus 2. So that's 5 times 1 divided by 4, and that's 1.25 amps. Again, if we use the idea of putting two things in parallel together, what we could do is take this combination of resistors and convert that into a single equivalent resistance. 10 in parallel with 20 would be the product over the sum. 200 over 30, that's 6.66. Current in I sub x would be the other resistor, R equivalent, over 20 plus R equivalent, and that would be 5 times 6.66 divided by 20 plus 6.66, and that would again give me 1.25 amps. So a couple of different ways of doing the current divider rule, using conductances or using equivalent resistances. And this is the definition of parallel resistors and the current divider rule.